Hey guys, welcome to episode 7 of Short Bits by Shorty. This one covers antifungals. Ooh, also, fun fact, this is the second to last video of the semester, or slash of P2 year. Holla, I'm so excited. Anyways, again, I'm only emphasizing the structure of the common scaffolds, or slash naming conventions, so I'm not going to be drawing all the structures for you to memorize. If I'm wrong about not memorizing all the structures, please feel free to slap me later in school. Also, again, Sunny might have a little appearance or voice clip in this little episode, like the last one. So watch out if he is or isn't here. So let's get started. So again, just for kicks and giggles again, here is the fungal cell wall. Outermost layer is the manoproteins. Going inwards, the beta-glucan. More inwards are your chitin layer. You have a lipoprotein between your chitin layer and your cell membrane. And your antifungal drugs target each of these layers to inhibit fungal activity. So, how do antifungal drugs selectively target fungi? Because they're both humans and fungi are eukaryotic cells. So how do you target fungi over humans? So one way is that they produce different steroids. So humans produce cholesterol, fungi produce ergosterol. And one big structural difference is that ergosterol, which is contained in fungi, have an extra double bond right here in the B ring. So this is the B ring. Might be a test question, IDK. Yeah, so cholesterol, as you notice in this B ring, doesn't have this extra double bond. So double bond is important. Let me circle that for you guys. So this double bond in green is important. So there's an extra double bond there. There's also an extra double bond here and an extra methyl group here. But most importantly, you have an extra double bond in the B ring, which allows antifungal drugs to selectively target ergosterol or aka fungal drugs. I mean fungi in general. Alright, so Amphotericin B is your first antifungal drug that we discussed in class. Here's the structure. May or may not be wrong, but you get the gist of it. There's a hydrophilic portion at the top, so all these hydroxyls are hydrophilic. And you have the hydrophobic layer at the bottom, which has basically no hydroxyls. Well, not as much as the top, and just double bonds, which are pretty hydrophobic. The mechanism of action is that it forms channels in the membrane via its interaction with ergosterol, and by forming channels, you leak important ions. So I'm gonna nerd out real quick because I thought this was really cool in class. So here's your cell membrane with all your ergosterols within it. Remember, ergosterols are selectively found in fungi, so Amphotericin B can selectively target fungal cells. So here's your amphotericin molecules with your hydroxyls pointing like this, and your hydrophobic part pointing towards the cell walls. So, as you know, like dissolves like, so polar portions of molecules interact with other polar portions of molecules. So here's your amphotericin, here's your also your amphotericin B. The hydrophilic parts of the molecules interact with each other through hydrogen bonds, because like dissolves like, so polar interacts with polar, and the non-polar portions interact with the cell membranes, because as you know, cell membranes have lipophilic or lipophilic or hydrophobic parts. So the hydrophobic parts of amphotericin interacts with the hydrophobic part of the cell membranes, which includes your ergosterols, because you know like dissolves like. So this forms a pore, as you can see over here, and ions leak out of the cell and causes fungal cell death. Isn't it cool? Sorry for my geeking out moment. So each channel contains over here 4 to 6 drug molecules, or 4 to 6 amphotericin B molecules. Anyways, hope you enjoyed me geeking out. Just really cool that simple chemistry can do some really cool things. Oh, and I don't feel like drawing the other natural products because that's going to take a while and I don't have that much time / I don't feel like it. But a lot of natural products like natamycin or nystatin, if you want, they're also analogs of or similar to amphotericin B. Just like for the hydrophilic part at the top and your hydrophobic part at the bottom. If you want to look them up yourselves, they're in the slide 9 of the antifungal PowerPoint. Natamycin and nystatin, they all have the hydrophilic part and the hydrophobic part. Oh, and they're also pretty long. So pretty long molecules with a hydrophilic part and a hydrophobic part. They're probably similar to amphotericin. So our next class of drugs are our allylamines. So our allylamines include naphthene and terbinafine. Ooh, forgot to underline it. Terbinafine. Ooh, pop quiz, top 300. Brand name for terbinafine. Lamisil. I only know that because I'm looking at it right now. You can tell these are allylamines. Well, you can tell this class of drugs. I drew them out because it's a class of drugs that has common scaffold. So this common scaffold is 2 6-member rings fused together. This is different from the quinolines if you saw my earlier video, or if you already studied that part, because the quinolines do have 2 6-membered rings, but in the quinolines, one is a nitrogen, the other isn't. In the allylamines, both of these are 2 6-membered rings without nitrogens. So the quinolines have 2 6-membered rings, one with nitrogen. The allylamines like naphthene and terbinafine have 2 6-membered rings both without the nitrogen. Mechanism of action. So here's a basic synthesis reaction of Ergo Sterile. Oh, forgot my parentheses. So Ergo Sterile is formed by squalene, which forms squalene epoxide by squalene epoxidase. So the mechanism of action of your allylamines is that they inhibit squalene epoxidase. So by inhibiting squalene epoxidase, you inhibit Ergo Sterile synthesis, thereby inhibiting cell membrane synthesis of your fungi. Also, squalene is toxic, so if you build up squalene in your cells by inhibiting squalene epoxidase, because you can't convert squalene to squalene epoxide, then you basically kill your fungal cells. Alright, so our next class of drugs are azoles, which include ketoconazole, voriconazole, stuff we had our rat on. So basic biosynthetic reaction of Ergo Sterile, like I said earlier up here, I'll show it again. So squalene is converted to squalene epoxide by squalene epoxidase. Didn't feel like writing the whole word because I'm lazy. And squalene epoxide is converted to lanosterol. Lanosterol is converted to whatever by 14-alpha demethylase, a CYP51A1 protein. And this X is converted to Ergo Sterile. Didn't feel like drawing or naming X because it's not important. So azoles work by inhibiting 14-alpha demethylase or CYP51A1. So basic reaction. So 14-alpha demethylase is important because it converts lanosterol to X by adding 3 hydroxyls to lanosterol and then eliminating these hydroxyls to form a double bond within X. So lanosterol is converted to X by the addition of 3 hydroxyls, then elimination of these 3 hydroxyls to form a double bond to form X. And this is done by the enzyme 14-alpha demethylase, a CYP450 enzyme, specifically CYP51A1. So azoles work by binding to the iron in the heme group of CYP51A1, and by binding to this iron, I can draw it for you. For example, this is just an example. This is not part of the actual structure of the imidazole, or the drug. But, so the target, azoles bind to iron and the heme in CYP51A1. So here is the heme group CYP51A1, this iron group. So imidazoles or triazoles or azoles in general work by binding from this imidazole ring to the heme group in 51A1. And by doing this, you prevent lanosterol from being converted to X by 14-alpha demethylase, or CYP51A1. By inhibiting CYP51A1 by binding to the heme group within it, then you inhibit ergo sterile synthesis, and by inhibiting ergo sterile synthesis, you inhibit fungal cell wall synthesis. There are two subclasses of azoles. There's the imidazole and the triazoles. You can tell the difference. I drew these because there's a common scaffold of these drugs. So you can tell the difference between these drugs because imidazoles have the imidazole ring right here, which is a 5-membered ring containing 2 nitrogens. Triazoles have 5-membered rings containing 3 azoles. So triazoles contain 3 nitrogens. Imidazoles contain 2 nitrogens. Remember, imidazoles contain 2 nitrogens in a 5-member ring. Triazoles contain 3 nitrogens in a 5-member ring. 1, 2, 3, 1, 2, 3. Both are 5-member rings. This is a 5-member ring. The difference between them is that triazoles have 3 nitrogens, imidazoles have 2 nitrogens. Hi, Sonny. So our next class of drugs are our 1,3-beta-D-glucan synthesis inhibitors. So biosynthetic pathway of the 1,3-beta-D-glucan layer of the cell membrane. So 1,3-beta-D-glucan is elongated to form the 1,3-beta-D-glucan polymer by 1,3-beta-D-glucan synthase and uridine diphosphate glucose, or UDP glucose. So echinocandins work by targeting 1,3-beta-D-glucan synthase. And if you target 1,3-beta-D-glucan synthase, then you can't completely extend 1,3-beta-D-glucan into the 1,3-beta-D-glucan polymer. So you can't completely form the 1,3-beta-D-glucan layer of the cell wall, cell membrane, I don't know. So if you do that, then you form an unstable cell wall, and the cell wall ruptures. Just a description said I don't think he'll test this on the structures of this class. These are cyclic peptides with lipophilic side chains. I also don't feel like drying because they're pretty big, and I don't think he'll be testing on this. But if he does, then feel free to slap me like I said. Okay, so our next drug is flucytosine. So this figure looks a little, looks like there's a lot going on in this figure, but I'll break it down for you. So, flucytosine is your actual drug. So flucytosine is a prodrug that's converted into 5-fluorouracil, or 5-FU. Not FU, but FU. You get it? Never mind. Okay. It's converted to 5-FU by fungal cytosine deaminase. And it's called fungal cytosine deaminase because, one, it looks like a cytosine, except it has a fluorine. So hence flu for fluorine, and cytosine because it looks like a cytosine. So flucytosine has a fluorine and looks like a cytosine. So there's a cytosine part. Deaminase part comes in because it deaminates or removes the amine at the top of flucytosine and converts it to an oxygen. So it deaminates the amine at the top of flucytosine and converts it to the oxygen in 5-fluorouracil. So therefore, that's how you get the name of fungal cytosine deaminase, and that's how you might remember the name. And fungal cytosine deaminase is not found in humans, so that's how you get the selectivity for fungal cells. So after flucytosine, the prodrug, is converted to 5-fluorouracil, 5-FU, it's converted into 5-fluorodeoxyuridine. Now, it's actually 5-fluorodeoxyuridine that interacts or binds to thiamidylate synthase. So that's why I put it in the box right here, because it's not flucytosine that is the active drug, active moiety. It's 5-fluorodeoxyuridine. So fluorodeoxyuridine interacts with thymidylate synthase. And by interacting with thymidylate synthase or inhibiting thymidylate synthase, you inhibit the conversion of deoxyuridine to deoxythymidine, and therefore you inhibit DNA synthesis. Let's see. So as I wrote here, the target is actually thymidylate synthase. So step 1, you convert 5-flucytosine to 5-fluorouracil. Then 5-fluorouracil is converted to 5-fluorodeoxyuridine. Now 5-fluorodeoxyuridine inhibits thymidylate synthase, and by inhibiting thymidylate synthase, you inhibit DNA synthesis. There's also a second mechanism by which 5-fluorocytosine or flucytosine acts. So it happens by the 5-fluorouracil pathway. So 5-fluorouracil is converted into 5-fluorodeoxyuridine triphosphate, not just 5-fluorodeoxyuridine, but 5-fluorouridine triphosphate. And this incorporates into RNA, and this messes up protein translations, since RNA is involved in protein translation. So, to sum it up, there are... also another important thing. 5-fluorouracil, some intestinal bacteria produce 5-fluorouracil, which can produce its toxicities. Anyways, so 2 pathways by which flucytosine acts. Number 1, flucytosine is converted ultimately into 5-fluorodeoxyuridine, which inhibits thymidylate synthase. And if you inhibit thymidylate synthase, you inhibit DNA formation. Sure. Second pathway, flucytosine is converted into 5-fluorouracil, and 5-fluorouracil is converted to 5-fluorouridine triphosphate, and this is incorporated into RNA, and this messes up with protein translation. So our last drug is griseofulvin. Griseofulvin acts by binding to tubules, and tubules are involved in cellular division. So if you bind to tubules, you inhibit cellular division, and fungal cells can't grow. Okay, so let's review everything I went over in this video. Hopefully this is also less than 20 minutes. Let's see. Ba-da-boom. Fungal cell wall, just for kicks and giggles. Also not for kicks and giggles, because it helps you understand the mechanisms of action. Drew it right there. These drugs are selective for fungi because of the Ergo sterile, which contains an extra double bond in the B ring, also an extra double bond here, and an extra methyl group here. But more importantly, an extra double bond here in Ergo sterile, which makes the molecule actually flatter. Let's see. First drug is Amphotericin B, which contains hydrophobic and hydrophilic portions. I don't know what happens to the sound part for this review part of the video, but it's not there, and I'm not going to try to record everything again because it's going to be a hot mess. But if you have any questions, feel free to let me know about this video or the last video. But here's my poll EV, pollev.com/CHRISTIANRUI629. Feel free to leave any feedback or start again. 1 star for 10 out of 10 would not watch again. 5 stars for A+ would watch again. Feel free to leave any comments, feedback, questions, concerns. I always take feedback, as you've seen from the last few videos. Good luck with the exam. Sorry again for the no review part. I don't know what happened to the sound part. But I hope you enjoyed this video and for Sunny's little appearance.